Hello directors, today we are talking about straight lines. We are on week 9, and first thing, set a timer, 5 minutes, number knockout. I think this week is our last week of number knockout, so enjoy that time of doing number knockout. We move on to something different next week. And then the next thing I do is talk about the compass page. So that's this page where they're showing where we are, which week we're in, which dimension, and they may have noticed that we have moved on to second dimension. Okay, and so you can ask them, okay, so if we talked about one dimension being a line, then how would we represent that? Well, maybe you could take your finger and pass it along, and then you could say, how would you represent two dimension? And so they might do some different things. They might like have one finger go up and one finger go over. More accurately, it would be one finger going forward and one finger going sideways. So something like that where they're going in two directions. That's pretty much the gist of what we want them to get. Okay, and then move on to the cover for the next 10 minutes. And so the cover has the print, the artwork from John James Audubon, so the American Flamingo, and just ask them, what do you see? And so hopefully they're going to tell you they see a flamingo. They might count how many flamingos they see in the picture. They might mention how they're seeing, you know, the curved neck, but that the legs of the flamingo are really straight. So you have these straight lines, and we're talking about straight lines. So maybe that's related. You probably want to point out that Audubon was famous for his drawings of a bunch of different birds. Let's see, he drew over 500 species of birds in his lifetime. And he's still kind of the guide mark of some of these images of what the birds look like. And then I just asked my kids, any guess what state he had to travel to in order to see the flamingo for the first time? And it was Florida. And then I said, has anyone seen a flamingo in flight? Or really most birds in flight? What do they kind of look like when they're up in the air flying? And they have their wings spanned out, and then they have their head, and then they kind of pull their feet down into their body, and they end up looking like a two-dimensional plane. So you have almost like a x-axis and a y-axis. It also reminds us of the cross. So the Christian cross. So, and as Christians, we believe we don't just have this one-dimensional solitary experience, but God designed us to be cooperative, to have our lives interact with others. So being part of a community, we're part of a community so that we may be iron to sharpen iron, encourage one another, and together accomplish what we could not do separately. And I think that all came from the conversation, which is right on the back of the image. And then there's the quote, so go ahead and I read the reflection first, and then I have the prayer echoes the importance of community. The prayer, Isidore of Seville says, and then the quote is from Charlotte Mason, and then it tells us that truth is joy, and the ultimate truth is God's truth. And then I said, do you guys know why flamingos are pink? Just kind of random little bit of fun fact, and actually some of the kids did know, and that's because they actually change their color because of their diet of shrimp. So they're more of a whitish color, but they turn that pink when they've been eating a lot of shrimp. So similar to how Christ takes our sins upon himself. So he's taking on something for us. So those were my correlations to things for that cover. So no more than 10 minutes, and then we move on to the invention pages. So the first invention page, that one, it's got some graphs on it and stuff. You could just open-ended say, tell me what you know about the second dimension. When I did the open-ended questions on my Talent Day class, I didn't find that a lot of them were just starting to throw a bunch of ideas yet. The older they get in challenge, it seems the more confident they are with that, but I didn't find like that my 12-year-olds were for the most part saying anything. So then I moved on to the common topics. And so I'll give you 5 examples for common topics. Of course, you don't need to cover all these. There's probably not time to cover all of these, but pick a few. So the first one, comparison. So compare 1D to 2D. So when we talked about zero dimension, we talked about a point, which had no length, no width, no height. And so that's our point. And we kind of put our finger to represent our point. And then in one dimension, we had the number line. I meant to bring out I had a little coffee stir stick. I forgot to bring it out. Okay. So I would have like a piece of string or, something to represent your one dimension, kind of like your number line. And so in one dimension, we would have infinite length, but we still don't have any width. We still don't have any height. That was one dimension. But in two dimension is like this piece of paper. So I have infinite length, but I also have infinite depth going back. I still don't have any height. So it's like a plane of paper, and you can think of this paper being composed of a bunch of lines. So an infinite number of lines going in one direction and an infinite number of lines going this way and this way, but no height to it. But because it's hard to draw on here and show you examples of graphs and everything, when I put it on the paper like this, we actually will draw our graphs and do all of our stuff, and then we're going to kind of rotate it and look at it upright, because that's the only way we can really look at it on our sheets of paper or up here on the board. So I think it's easy for kids to mistake and think that the height is what becomes infinite when we're in 2D, because we're looking at graphs that are like this, but this is really laying down like this. Okay, so your X is kind of like your infinite length that we had in 1D, and then your Y is this infinite depth that goes back or comes forward. We still don't have any Z. We're not going up in height yet, but we've tilted it so that we can actually see it and work with it. That's a concept I think maybe they don't always understand. Okay, and then it looks like I made a little note that with when we were dealing with like the number line, when I have 2 with an exponent of 1 is just 2. So this is the concept that we have, like, 2 boxes. But once we get into 2 dimension, now we're starting to take up more space. And so this is kind of like with 2 squared, you get 4 boxes. So now you're stacking this and you're getting more dimension. Okay, then the next common topic, define line versus plane. We kind of just did that. So our line, infinite length on our line, but no width or height. And then the plane has a bunch of these guys, and they're infinite lines all going in one direction. And then you also have your infinite depth, and these are going in this direction. And so all these lines with their infinite depth and their infinite length are making up your plane. And so planes are a 2D concept. Third common topic, circumstance. How do the circumstances of the coordinate system determine the variable used? Okay, let's write out. You see those variables on that invention page, but this is just the idea. This one we're probably most familiar with. X and Y axis. So this is X in a positive direction. This is X in a negative direction. This is Y in a positive direction, Y in a negative direction. And then we would be looking at points along the way. So let's say if this is like 1, 2, 3, 4, and this is 1, 2, 3, 4, I could have a point 4 on my X and 4 on my Y, and I'd get to that point right there. On the polar coordinate plane, okay, this is meant to be the center of my circle. So I have a circle, and this is meant to be the center. I don't think I drew that very well on center, but pretend that's the center. Okay, the distance from the center to the circumference of my circle is my radius. And then if I have some other point on the circumference, say up here, and I go from there to there, that angle right here, let's say this is 50 degrees, we call that theta, and it looks like that. So when we are talking about X and Y, those are the things for our coordinate of a rectangular plane, rectangular. And when we are talking about radius and theta, Those are the points we use on our polar coordinate plane. Okay, that's all I have on there. Next thing, relationship. Discuss the order of operations as an example of relationship. And I just put in my notes, we need to complete one step before we move on to the next. I'm not sure any more detail on that. So that must have come though from the tutor training. So, and then the last thing, consider the authority of points. Okay, so here's that idea. When you have one point, you can have an infinite number of lines going through that point. Okay, I can keep drawing these. Infinite number, it can keep going, it can keep going. But the point when I have 2 points, I now only have one line that can go through those and touch both points. So 2 points will give me a line. If I add a third point, all I need is a third point, and now I have a plane. Because I have this going in one direction, this going in another, and now I have infinite length and width, and so now I have a plane. So if you have 3 non-collinear points, you're going to have a plane. 2 points is just going to give you a line. You could still be in one dimension. And then 1 point has infinite lines. And that comes up in their questions that they do. All right. The next thing is the memoria and arrangement. And that's the page where you actually see a linear graph. And I just put on the note some lines, some things that are helpful to memorize the form of lines. So things that I would talk about here would be, so y equals mx plus b. I would talk about slope. So this is your standard line for a slope, for a straight line. So here we have the m represents our slope, and it has that listed on here too. And so the slope is also the same thing as saying your rise over your run. And the rise is your change in your y values, yes, over the change in your x values. Okay, let me draw this on the actual coordinate so you can see this. Okay, y, negative y, and there's my positive x and my negative x. Okay, 1, 2, 3, 4, 1, 2, 3, 4. Okay, if I say that every time, well here, let me give you an equation. Y equals x. And if it's been a while since you've done that, hopefully this helps it come back to you. I'm going to look at the example of y equals x. So this is saying every time I have a value for y, it's going to be the same value in my x. So if my y is 2, my x will be 2. So let's go look over here. If I go to 2 on my x, that was 1, 2 hops over, and then I go up 2, 1, 2. So 2 and 2. Over here, if I have a 1 on my y, that would mean I have a 1 on my x. So 1 on my x and 1 on my y, I put that right there. If I have a negative 2 on my y, I have a negative 2 on my x. Let's see what that looks like. Negative 2 and negative 2. I put that right there. If I connect all of these, I only needed 2 points to connect. That's what you're looking at here. The change in y means looking at the difference in the y. So this y was at 2, this y is at negative 2, and so you could look at that change of 4 steps, and then my change in x is from the positive 2 to the negative 2, and that's also a change of 4. So in this case, looking all the way from a point where I have 2, 2, and 2, 2, my change in y has been 4 steps, my change in x was 4 steps. You divide those and it just equals 1. It's just a positive 1. And that is true that my y equals x line is just going to be a straight line that looks like this. Now it follows this original slope equation, or original line equation, because, let me just erase some of this. In this case, my y's equaled my x. We calculated how the change in the rise over the run, the change in the y over the change in the x was just 1. The value was just 1. So that's like my m right here. And then plus b, oh, I forgot to point out, b is your y-intercept. Intercept. So that means where do I intersect with this y-axis? And in this case, I'm intercepting right here at 0. And so b was just 0, which it indeed was 0 in this example. If my b had changed to 2, okay, if I had come over here and changed my b to 2, but I kept everything else the same, plus 2, that means I'm starting right here. That's where my y-intercept is, my b value, but I'm still going to have a parallel line that comes through and does the same thing as this line had done. It's going to have the same slope, the same direction. And so when I was trying to have my kids think about slope, I was just pointing out that positive slope is going up, and I actually drew a little picture of my, here's my Superman with his cape. Okay, he's flying up, so it's a positive slope. Here, his slope is constant, so he's just flying forward. And I'm a really bad artist, so my kids loved this. And then if he's heading down this way, this is a negative slope. He's heading down at this point in time. All right, okay, so that's a lot for forms of lines, but if you can start to cover some of this, it's going to help them out in understanding what they're looking at. The next thing I put on here are useful things to memorize, because there's a lot on that page and they don't necessarily need it all right now. This is helpful to memorize, is that with your x and your y axis, that this first part up here we call quadrant 1, and you can just represent it with a Q1. This is where you have a positive x and you have positive y. So all these values are positive for the x and positive for the y. Q2 is negative x, still positive y. If you can get them to memorize those two, for the complex kids, they're pretty much staying in these two quadrants for their problems. So that's pretty good, but you might as well just show them. There's more quadrants. So quadrant 3, or you might have these as little Roman numerals. I think they throw them in as Roman numerals. So let me switch that. I've seen them both ways, so. But if we want to stay consistent, there we go. Okay, quadrant 3, so negative x, negative y. And then quadrant 4 over here is positive x and negative y. So if they can start to see how those quadrants tie together, and if it's, positive x or positive y, that's going to help them, because then as they have values for x and y, they can just quickly say, oh, I know that's going to be somewhere in quadrant 3, because those are negative numbers, all negative numbers. Ways to graph a line is the next thing I wrote. I just showed you how to do that, where you can have the example of y equals x. It's the easiest equation to use to show them how to plot a line. And so then you plug in a value for y, you see how it's the same value in x, and then you can chart it on there. They're going to learn and start seeing more complex equations and what those different lines look like. But for this week on the introduction, I would just stick to the simplest equation you can use, y equals x. And then it also mentions on this page midpoint formulas. They've seen that before. That was back, I don't know which week that was, but they were calculating midpoint even on the number line. And you can just point out that you can have midpoints now, even though your lines are going up in some other direction. All right, arrangement. Okay, yeah, the relationship of the quadrant, and if it's positive or negative for x and y values will help you remember it. And that they should not worry about trying to like memorize this specific one line. It's just meant to give an example of what some of these words are and a definition of it. But there's nothing special about this one particular line, other than it shows a nice little y equals x line. All right, charts. So chart stuff that was mentioned is key concept for the week, 2 dimension. So just understanding how 2 dimension is stretched or stacked lines to build a plane. So that's the idea that we have a bunch of lines going this direction, we have a bunch of lines going in this direction for our width, our length, and we have a bunch of lines going in this direction for our depth, and together that builds the plane. And plane, like that. And then definition of a line, an infinite number of lines can be drawn on the coordinate plane. That's this. 2 points determine a line. Okay, yeah. 2 points determine a line, you can have that in 1D, but 3 points can give you a plane. All right, that was quick, that was easy. Okay, aha moments from last week. If they have stuff from last week on equations that they're working through or they need help on. Going through the tops. Oh, I wanted to point out something on the tops because I was looking through the tops of the pages. The top of page 1 has absolutely no work for the students to do, okay? This is like giving them information and definitions. So for your first group that's doing this page, I would have them do this second section, because that's the part where they're actually having to answer something and do something. And then the next 3 pages are nice because they are an introduction to different ways to graph items. So there's page 2 has linear graphs and notation. That's kind of like what we did in our example. The page 3 are function graphs. So those inequalities that we've talked about, that we did on the number line, and we talked about union and intersection. Now we are looking at those inequalities in a function graph. And so function graphs are a little bit different. We're shading part of the graphs because that's when you're including something on the graph, you're including the section that you shade. That's what they're starting to see here. And then on the page 4 are vector graphs. So we're just talking about making graphs, but using vectors to make those graphs. And vectors make a lot more sense and are more fun because now we are in 2 dimension and we are moving in multiple ways. I don't think they talk about I. Okay, they don't talk about I in here, but hey, for you directors, I'm just gonna throw this little thing to you too. We saw in 1 dimension, we had the real number line, right? And we were moving along. And then we would have separate problems. And they had this imaginary number line. So we had our imaginary number line. 2 dimension is the point where those 2 can intersect at the point of 0. And so now they can intersect, and you can have, in our 1D, we only had numbers that were somehow imaginary, 2i, 4i. And we stayed along the number line. Although when we started doing our calculations, sometimes we would calculate things and end up back in the real point. Anytime you're doing those calculations and you move off, and sometimes like you're over here now and you're at 1 or you're at -1, this is where it went back into the real number line and back into real numbers. And so 2D is when our imaginary numbers and our real numbers are coming together, and now we're really looking at complex numbers. And I'll link below to the, I'll put in the comments the link to the rotational illustration of how the real number line and the complex number line work together, and that's how we get our, when I say that I squared is -1, what I'm talking about is that we're making those 2 rotations over here to -1. So I'll link to that video because it's like 10 minutes on its own, and I don't want to bug you with that now if you've already seen that. All right, remind them of seeing the unseen, go through the catechism. And then it looks like this week I did throw a few examples of some things to add if you're not already doing them for the notation note cards, and that's the slope, variable x, variable y, quadrant, and then the B as the symbol for the y-intercept. All right, and don't forget a Math Explorers program. So if you want more help understanding the 2D, or your students do, or they need more help on the planes, and then the 3 different videos I have go through the different types of the graphs. So the linear graphs, and then the function graphs, and then vector graphs. So thanks for everyone who's using that and all the feedback. It really helps. And I think that's it.